The topic of today's lecture is boundary integral equations. So the idea here is that we're given some sort of second order elliptic PDE, which I write in the form here. Omega is just some domain in R2. You can think of it as being smooth. It has gamma, or boundary I should say, gamma. Something like this. So for simplicity, let's just consider Dirichlet boundary data. So the idea then is that in many situations you can write an equivalent equation. So instead of working with a PDE, we can formulate a boundary integral equation. So this is an equation that involves a different unknown function that we call sigma of x, and a typical equation would look something like this. And the point here is that this equation is defined only on gamma. So the unknown function sigma is defined on the boundary gamma, and the equation is set on gamma as well. K is some sort of kernel function. We will explain in additional detail later what this is. So the idea is that instead of solving the PDE, you can solve an equation like this, and once you've solved that and determined sigma, then typically we can recover the function u of x by integration, sometimes using the same kernel, sometimes a different kernel. But basically, once you've computed sigma, you can recover u by just some basic integration formula like this. And why would you want to do this? So the obvious advantage is in a situation like this where you reduce the dimensionality. So the equation up here, we see that the PDE is one formulation of the problem, and this is in some sense equivalent to the boundary integral equation. And we see that an obvious advantage is that the PDE here is set on a 2D domain, and the boundary integral equation is set on a 1D domain. So the number of degrees of freedom you would need would scale for the PDE as basically 1 over h squared, and for the boundary integral equation as 1 over h. So h here is the mesh refinement, like how finely do you discretize things in space. So this is a clear advantage. On the other hand, you get when you discretize the PDE, you get a sparse system A, whereas when you discretize the boundary integral equation, you get a dense matrix A. So this is something we'll need to deal with later on. Okay, so this is just a very brief introduction. What we're going to do is that we're going to go through a few special cases. So we'll start with just illustrating how to do this for some specific PDEs, starting with Laplace equation, and then we'll move on to Helmholtz equation. And with each of the examples, we'll illustrate one problem or one benefit that might arise using boundary integral equation. All right, let us start with a Dirichlet problem associated with the Laplace equation. Okay, so here is our first example. So omega here again is just a domain in R2. And what we're going to do is that we're going to look for a solution to the PDE that takes the following form. So it's an integral, so we're looking here. So it's an integral over the boundary. Sigma is some function that lives on the boundary, and we're looking for a solution that takes the following form. And s of xy in this case is the kernel function. So this we recognize is just the this is just the fundamental solution of the Laplace equation in 2 dimensions. So the main point here is, let us write a little claim. So the function u is harmonic in omega. So in other words, Laplace u is equal to 0. So why is that? Well, first of all, if we take a point y on the boundary, and then we take some little surface element delta s, and then if we look at the function x maps to minus 1 over 2 pi log x minus y sigma y delta x. And what is this? So this is the field. This is the harmonic field that's generated by a point source at y of this strength. So this is the field generated by sigma y delta f. So now if you integrate over the entire boundary, you just integrate all these things along the boundary, then this of course is a superposition of harmonic functions, so x here, it's just under the integral in the definition of u. Differentiation under the integral in star. So in other words, if u is defined by star, then if you apply the Laplace operator to u, then you would want to have that this can just pop underneath the integral like this, and then this is 0, right? Because if you look at the function s, then for a fixed y, if x is removed from y, then this is a harmonic function of x. Okay, so this you can certainly do because the kernel function is it's a z infinity function. So if sigma is just integrable or something like that along the boundary, then you can easily justify this differentiation under this sign. All right, so as long as we define u by this expression here, or actually let me remove that. So as long as we define u by this expression, I mean, this will for sure be a harmonic function inside omega. So the question then is just, do we satisfy the boundary condition or not? And for that, we need a second claim. So the second claim is that the u defined by star, the u defined by star is a continuous function. So as you move x around, whether you have an x there, maybe we have an x here, maybe wherever you put it, this function, again, this function here, is going to be continuous as a function of x. So s has a singularity. As x and y approach each other, this is a singular function. So it's not entirely obvious that the function u defined by star is a continuous function, but it turns out that this singularity is weakly singular. You can just integrate it straight up. So it's really not a problem. As you move the target point x around, it will be continuous. So in particular, what I mean here is that if you take, or what I should say is that if you fix an x on the boundary, maybe I should stick to black. So if we fix an x on the boundary, then what this means in particular is that u at x, this is just the limit as x prime converges to x for x prime inside omega, u of x prime. And this is just given by exactly what you would expect. So in other words, what this means is that if we can find a sigma such that the following equation holds that f of x is equal to integral against sigma, and this must hold for all x and gamma, then u satisfies or I should say u as defined by star, satisfies the PDE. Okay, so let's call this equation here BIE, and then the bottom line here is really that PDE and BIE are equivalent equations. So, if you think of this as a modeling an electrostatics problem, so you have, in that case, U would be an electric potential, you specify its values on the boundary, and the point here is really just that there are two equivalent ways of formulating that as a mathematical problem, that the PDE is the one that we're perhaps the most used to, but this boundary integral equation is also a perfectly legitimate formulation of the same equation. And BIE it's a very natural equation, right? Because the input data you're given here is gamma, which is a one-dimensional object, and you're given the function f. The Dirichlet data is another one-dimensional object. So, in some sense, the boundary integral equation is you have one input data, you're looking for a 1D output data, in this case sigma, and in that case you should have an equation that really only involves one dimension, and that is precisely what the boundary integral equation provides for you. So next we're going to talk about conditioning. So in the next example we're going to compare the conditioning of the two equations. So if we start thinking a little bit about the partial differential equation, we recall that the Laplace operator as a differentiation operator is an unbounded operator. So when you discretize this, you're going to have to end up with a matrix that's ill-conditioned if it's going to capture the eigenvalues of A to any accuracy at all. So in particular, if age again is the, maybe I should make some notes here. So to continue here, I wrote down some notes. So recall that if you discretize a PDE, you get a sparse system like this, and the condition number of this sparse system typically scales as 1 over h squared. On the other hand, if we look at this boundary integral equation that we derived on the previous slide, it turns out to be a better condition. It has conditions, so you get a linear system like this that's smaller because you have fewer degrees of freedom, and it's also better conditioned. It has condition number 1 over h. But it turns out that you can do much, much better than this, and that is the objective of our next example. Let's pause here. Okay, so let's continue. Here's the next example. So it's exactly the same PDE as in the previous example. We have a Laplace equation with Dirichlet boundary data. The only difference is that now I make an ansatz. I'm looking for a solution u of x to that equation that takes the following form. And the only difference compared to the previous slide is that I now picked a different kernel function. So this d of xy, it looks as follows. It is x minus y dot n of y. And what's n of y? Well, for boundary point y, n of y is the unit normal vector. So this function, you can view this as a normal derivative of s of xy. So s of xy was the log function, it's just a standard fundamental solution, and this is really the normal derivative. So you can view this, so what is u? So u is really a, you can view it as a collection of dipole fields. So if you fix a y on the boundary, and then we consider the function d of xy, sigma y, and then some little boundary element like that, what is this? Well, this turns out to be the field generated by a dipole of strength sigma of y located at y. So this is a dipole field. So the bottom line of this is that exactly as before, using a similar argument, you can prove that this function u is harmonic inside of omega. So, or alternatively, you could differentiate. You could take this expression for u of x. You could differentiate under the sign. You need to moderate this, but that's not difficult. And then you can show that this function D here is harmonic. If y is on the boundary and x is some point in the interior, then d of xy is a function that's harmonic in x. This is very just it's field with a Laplace operator. You see, you'll get 0. So let us summarize this. I'll clear the slide a little bit like this, and then let's just put u defined by star is harmonic. So the intuition is again just based on it's a superposition idea. It's a superposition of fields generated by dipoles. You want to prove it mathematically, then must differentiate under the is not continuous over all of R2. You'll notice that here I restricted the applicability to be just x in omega. And the reason for that is that this is it's a C infinity, it's a harmonic, very nice function on omega. You could also define it for x outside of the domain, and it would be harmonic there as well. But the limits of the two values, if x approaches the boundary from the inside, or if it approaches from the outside, you get different values. They have different limit values. And there's a discontinuity there, and if you take an x that's actually on the boundary, you get a third value. So there is some trickiness here. And the claim is the following. So if we fix x on the boundary, then the limit as x prime approaches x, 0x, so u here is defined by star. As the limit as x prime approaches x, this turns out to not be just plugging in x in this expression. Instead, you get the factor 1/2 of sigma of x as integral gamma dx y sigma y dx of y. So the point here is that we now got this new term popping up here. And this main issue, so this represents the jump. So as you approach, the point is that if you take an x and you approach with x prime, so you took an x on the boundary, if you take x prime and approach it from the inside, you get one limiting value. If you approach from the outside, you get a different limiting value. And if you evaluate this integral for x actually on, you get a third. And these values change. They're different by precisely the value of sigma x. So the difference between the limit on the inside and the outside is sigma of x. And if you put x exactly on the boundary, then you get half of that. So this sort of looks problematic. All right, not problematic perhaps, but it looks like it's more dicey to work with. But you'll see now that the point here is that if we can find, let me phrase it like this, if we can find a sigma defined on gamma such that minus 1/2 sigma of x plus integral d of xy sigma y ds of y is equal to f of x, and this needs to hold for all x in gamma. Then u defined by star solves PD. All right, so now I need to rearrange my slide a little bit because I want to have space to name this equation. So let's call this equation BIE to be consistent. And here we had gamma is the boundary. Okay, so BIE is sort of equivalent formulation to PD. And now the beauty here is that BIE is a second, this equation here is a second kind Fredholm equation. Let's write this, yeah, let's keep red, this is good. So BIE is a second kind Fredholm equation. So what does that mean? So a Fredholm equation, so we can write that as follows. Where D is a compact operator. On, say, L2 of gamma. Okay, so here I maybe jumped a little bit ahead. D is an operator that acts on gamma, and it's just integration against what's called a double layer kernel D. Okay, so this is for x in gamma. So the point is, what we did here was that we defined an operator capital D. So what capital D does is that it takes a function sigma that's defined on the boundary gamma and it maps it to a different function that's defined on gamma. And if you view that as an operator from L2 on the boundary to L2, this turns out to be a compact operator, at least when the boundary of omega is smooth. The statement basically holds for piecewise smooth boundaries as well, but it gets a little bit more technically complicated. So let's just consider the case of a smooth boundary for now. So in that case, this operator is compact. What does that mean? So that means that to any precision epsilon, you can find a finite dimensional operator that captures the action of D to within precision epsilon. So you can approximate D in operator norm. So within precision D epsilon, for any epsilon by a finite dimensional operator. So that really means that this equation here, it is an equation on an infinite dimensional space, but it is as close to a finite dimensional equation as you could possibly get. It's essentially, for any finite precision, this is just a matrix equation. It's a finite equation. And it also means that the condition number, so this operator minus 1/2 plus D, it's just a perturbation to the operator minus 1/2 times identity. It turns out to be non-singular, so you can prove that this is 1-to-1 and onto. And that means that it has some finite condition number. And that condition number typically is not that large. And when you discretize this and you get a system, you get some matrix system. So if you discretize this and you get some linear system B sigma equal to F, then the condition number of B converges as you refine the mesh. So as you use finer and finer spatial discretization, the condition number of B turns out to converge to the condition number of this equation, because the continuum equation has the finite condition number in this case. So this is all very, very nice. And we'll see in some numerical example in the following lecture just how nice this is. So oftentimes the condition number is 7 or something. If you use GMREFs to solve the corresponding discretized system, it converges to double precision in a dozen iterations or something. It works really extraordinarily well. So now there is one thing that we might worry about, and it is the following. So D, or let me phrase it like this. So let's look at the definition of D here. So now it might seem as if D, as x approaches y, it might seem like the numerator scales as absolute value x minus y, and the denominator scales as x minus y squared, which is starting to look a little iffy, right? So it seems like this might scale as 1 over absolute value x minus y. And this would be very problematic, because that would not be an integrable function. The integral of this absolute value, if I fix an x and I start integrating something like that, I'm going to get infinity. This would not be pretty. It turns out that's not quite how it works. So let's see on the next slide what actually happens. We continue. All right, so what we had was, remember we had defined a function u like this. D was the what we're going to call a double layer kernel. It looks like this. And the problem was that it looks as if D is quite strongly singular. But suppose we fix point x on the boundary, like so. Then it turns out that this actually approaches a finite limit value as y approaches x. So what is happening here? Well, so if we take a point y somewhere on the boundary, and then we have the unit normal vector n of y. So here is the vector x minus y. You see that the angle here, alpha, so alpha converges to pi half as y converges to x, right? So that is to say that, so what this means is that x minus y dot n of y, this does not converge as absolute value x minus y. Instead, it's x minus y squared, because this vector goes to 0, but in addition to that, the angle between the two vectors goes to pi half. Right. So we actually have the same strength in the denominator as in the numerator. So what this means is that the limit as y approaches x, let me rewrite, the limit as y approaches x, when y is restricted to the contour gamma, d of xy, it's some finite value. And you'll find more information about this in the lecture. I don't want to do the detailed derivation. This function is actually C infinity. So this is quite remarkable. It's not often in boundary interequations that you get kernels that are actually smooth, but this is a particular case. So we're going to use this in some numerical examples and in some of the homework problems. But this is not typical. It's a special case. But it's a very nice special case, and it's good to know about this stuff. All right, so this kernel, it's extremely benign. Let's go back and look at the previous slide. So this formulation is really very, very benign. You have a second type Fredholm equation, you have a C infinity kernel. We're going to see that we can discretize this using very simple techniques. It's not quite representative of boundary interequations in general, but this will be very handy for us. Let's do another example. Let us continue by looking at a Neumann equation, or a Laplace equation with Neumann data. So just as before, we have a 2D domain, omega. It has boundary gamma, and everything is the same, except for now we have the Neumann boundary condition here. What we do then is that we look for a solution in the same form as the first time when we approached the Dirichlet data. So we have this, we make this ansatz like that, where S again is the single layer potential. So just the fundamental solution associated with the Laplace equation. And just as before, we have a claim that U defined by star is harmonic in omega. So that works exactly as before. The second claim is that if you evaluate the normal derivative of the function defined by star, so let U be defined by star, then du dn, I should say, let's fix an x on the boundary, then du dn evaluated at x, well, what does this even mean? So this, what we mean specifically is that if you take the limit as x prime approaches x, when x prime is restricted to the interior, so what's going on here, so we have some point x on the boundary, we have an x prime in the interior, and as that approaches x, what is du dn? Well, this is the normal derivative, the normal at x times the gradient of u defined by x prime. So u here, observe, so this function I mentioned earlier that it's continuous everywhere, but it's not smooth everywhere. It's smooth inside of omega, it's smooth on the exterior, but it's not smooth across the boundary. So that means that the normal derivative essentially has to jump. So we have to be careful. So if you take this function, if x prime is an interior point, then you can certainly just differentiate. You can just apply the gradient with respect to x underneath the integral sign. That's perfectly well defined. If x prime is the interior, if you take the normal derivative, if you take the inner product of that with n of x, then you get a function that has a limiting value, and the limiting value looks something like this. So refer to the lecture notes for the signs here. But it looks like that, where d star is a close cousin, or rather the dual, of the double A potential. So this looks like this, as follows. All right, so it's exactly the double A kernel, except that now I have n evaluated at x. It's not n of y. But other than that, it's the same kernel. So the point then is that the BIE we get, so we seek a sigma such that 1/2 sigma x plus integral over gamma d star xy sigma y ds of y is equal to f of x, and this needs to hold for all x gamma, and this is my BIE. So BIE is equivalent to PDE in this case. And moreover, the boundary integral equation is a second-kind Freedom equation. Like this. So everything is basically as nice as for the Laplace problem, but there is an important caveat, which is that BIE has a one-dimensional null space. And it is not onto. And if you think about it, that really has to be the case, right? Because the PDE is not well defined in itself. So the solution is not unique. It has the PDE itself has a one-dimensional null space, which corresponds to just shift by a constant function. And it doesn't have a solution for every f. You have to have integral f equal to 0 over the boundary. If you don't have that condition, then this equation does not have a solution, and the solution is never unique unless you do something to lock down the invariance for a shift by adding a constant. So the PDE has one-dimensional trickiness you need to deal with, so of course the boundary integral equation does as well. But that can all be done. Our next topic is to describe integral equation formulations for exterior problems associated with the Laplace equation. As a warm-up to that, let's just remind ourselves how things work for an annulus. So consider an annular domain omega, so it's the domain between two circles, so radii lowercase and uppercase r respectively. So in this case, it's very natural to work with polar coordinates like we have here. And then let us write down the solution. So the solution looks like this. We have some terms that are constant or decay as r goes to infinity, and we have some that increase as r goes to infinity. So then we need to match these with the boundary conditions. So let's say we expand f. So say at r, f has a series expansion that's similar. So f, of course, lives only on a boundary, so it has only theta dependence. We'll write it like this. And at capital R, let's say it has exactly the same coefficient, just uppercase. So the solution looks like this. And then, of course, all we need to do is we need to match the corresponding Fourier modes. So if we have, so for the looking at the terms that don't depend on theta, if we set x equal to r on the inner condition, we see that C0 needs to match lowercase a0 plus uppercase a0 times log r, and then at the outer boundary we get uppercase C0 is equal to the same thing but with uppercase r. Okay, so here's the linear system that allows us to determine lowercase a0 and uppercase a0. And then, of course, you have similar things for the cosine and theta terms. What do you get? So we have lowercase cn and uppercase cn, and they are respectively an 1 over rn plus an rn. Now, so you get some stuff here. So basically you just match terms, and we see that in general all of the coefficients in the general solution are necessary, because we have one Fourier expansion on the inner circle and one on the outer circle. Now the question is, what happens if we let capital R go to infinity? So what if we don't have the outer condition? Then the natural thing to ask for is that we want all these terms to vanish. So we're looking for a bounded solution. But one could also keep just the first term. So let's look at this on the next slide. So let's consider the Laplace problem on a domain that's exterior to a disk like this. So now we have the outside domain here, so omega is all this stuff. Right? So then we have the same equation. Here's our PDE. Here is the Fourier expansion of the boundary condition. And now the question is, what is the natural solution to this? So in principle, if you write in polar coordinates, we had all these, both the terms that increase and decrease, and oftentimes the natural solution that you want would be u of r theta would be a0, and then typically we want just the terms that decay here, like this. So that is oftentimes the natural solution, and for that solution, the appropriate third condition up here would be supremum u of x is finite for x in omega. Right. So if you have this red additional boundary condition at infinity, then that would be the natural solution. Sometimes, though, let's just point out that there's another solution. It's also perfectly natural to ask for. So we might ask for the solution u of r theta, where we keep these decaying terms, but maybe we want the log term here. So we have this function, and how do we find what is the boundary condition that leads to this one? And then typically this would be corresponding to the following, that there exists a Q such that the u of x minus q over 2 pi log x goes to 0 as x goes to infinity. So that's the condition that leads to this equation. And this is oftentimes in physics a natural solution to look for, because if you say you want a field that corresponds to some set of point sources in here, then capital Q would be the sum of the point sources inside, and you might naturally want to look for a solution that grows logarithmically at infinity. All right, so this is just a brief recap of appropriate boundary conditions of Laplace at infinity. So next, let us consider a Laplace problem with Dirichlet boundary data on a domain that's exterior to, in this case, a general contour, gamma. So previously we talked about gamma being a disk, in which case we could write down the solution analytically. But let's consider this general problem, and we do this boundary condition at infinity, so to speak, in red. So in this case, there are several different ways of formulating this as a boundary integral equation. So option one would be, of course, to just look for a solution in the form of a single layer potential where, as before, the kernel is really just the fundamental solution for the Laplace equation, just like that. And then the resulting boundary integral equation, because this u that I just wrote down, it's continuous, so following exactly as in the case of an interior domain, you get everything just basically looks exactly the same. So there's your boundary integral equation. This is well posed. It's easy to formulate. But it's ill conditioned. Just like the interior problem. So then, the natural thing to do would be to look for a double layer formulation. Like this, where the double layer potential just as it looks just like before. And now I'm not going to make any promises on signs, but usually I like to define the normal like that, so pointing into the domain in this case still. And this, you know, in principle, this works very well. We would get an equation that looks like this. So you would get a BIE very standard, like that. So you get a second Kern-Friedholm equation. But there's a problem here, which is, well, if you look at this kernel D as x grows, you see that the following thing happens, that as x goes to infinity, we find that the absolute value of d, x, and y will scale as 1 over absolute value x. Not sure what this little thing is. Okay. So what does that mean? So that means that u, your solution u, will be bounded by something like the integral of the L1 norm of sigma divided by x, maybe some constant 1 over 2 pi or something. So this means that your solution u will decay, which means that there will be solutions you'll miss, because you have to keep either the constants or the logarithmically growing terms. So the problem here is that star does not represent all solutions. Which is quite problematic. So we can't really use this. We have to do something different. So let's backtrack a bit. Let's remove all of this. And I'm going to need a little bit more space. So let's rewrite d of xy. Because what I want to do is I want to add a term here. I want to add a term that goes as log x. So what I'm doing is that to add u, I'm adding this term over here. So what is this? So this is the field from a point source located at the origin. So I'm assuming that the origin is inside the contour here. Otherwise, you just need to include some arbitrary point inside the contour and do x minus that arbitrary point. So I'm adding here the field from a monopole centered at the origin of strength equal to the integral of sigma. And if I do that, then it turns out that the boundary integral equation you get takes the following form. So you get this equation. So let's just bake that kernel in, or this term into the kernel. So we get the following equation. So if we assume that this has to be satisfied, so here's the boundary interval equation. Now this is a second-kind Freedom equation, and everything works very well. So now PIE is, in a strong sense, identical to the PDE. They both represent the same set of solutions, the same set of f's are permissible. I see I realized I forgot the data here. So this should be equal to f of x for x and gamma. So let us summarize. So what are the advantages here? So what's the purpose? So advantages of BIE. So what do we have? So we have the reduction in dimension. So 1D domain instead of 2D. We have a second-kind Freedom equation. It's well conditioned. And finally, we now have finite domain. So the boundary condition at infinity is satisfied automatically. And this last point is really quite important, because if you think about it, say you wanted to solve this PDE. Say you have this problem, and we want to solve that using standard formulation, say finite elements or finite differences or something like this. Well, what would you do? I mean, one idea would be to enclose your domain omega into some artificial external boundary. And then you set some boundary condition here, and then you now solve in a finite domain. But generally speaking, it's really quite hard to figure out how to use standard PDE discretization techniques on an infinite domain. There are lots of methods that have been proposed, but in a case like this, the boundary integral equation formulation really has a very persuasive advantage. Our next topic is boundary integral equations for the Helmholtz equation. And as a little warm-up, let's just review some basic properties of the Helmholtz equation. And we'll do it for 1D. Everything is very easy in 1D. So let's just see. And let's start with Laplace, just to set a benchmark. So Laplace problem in one dimension is, of course, very simple. It's just that the second derivative of u is 0. So we have some boundary conditions on the left and the right, f0 and f1. I just arbitrarily chose 0 and 1 as the sides, as the start point and the end point of the interval. We know that the solution to this very simple PDE, the general solution, is just a straight line. So, right, so there we have u. It is just a straight line between the 2 points. And everything is very nice here. So this is well posed. And we have a maximum principle for this problem as well. Which is to say that the max and the min of the solution is attained at the endpoint. And this holds for 2D problems as well. So Laplace basically is very nice from this. Next, let's look at the Helmholtz problem. So here we have minus uxx, and then we have an additional term like so. Otherwise, everything looks exactly the same. So the difference here is this term. We now have a constant term. And this makes quite a difference as it happens. So if we take our boundaries 0 to 1, then what's the general solution? Well, this is A times, now we have oscillatory solutions, cosine and sine functions. So how do we find A and B? Well, we get a linear system, which is if you plug in x equal to 0, you get A is equal to f0. If you plug in x equal to 1, you get, no, you don't, you get A cosine kappa plus B sine kappa is equal to f1. So we can write this as follows. This is a 2 by 2 linear system. Cosine kappa, sine kappa, AB is f0, f1, like so. Now, the interesting thing is that this, the determinant of this little matrix is sine of kappa. Times. If kappa, to be precise, is equal to pi, if it's 2 pi, 3 pi, and so on, then system is singular. There are sometimes no, the solution is never unique, there are sometimes no solutions. So what does this mean? We know precisely what this means. For instance, so the first singularity looks like this. So this is sine pi x, and we see here the sort of the problem that happens, that if you're at one of these bad points, kappa equal to pi, then you have a solution, a situation where you can have 0 Dirichlet data and a non-zero solution, which of course means that if you have permissible Dirichlet data, then you can always add a solution like this. So the problem happens precisely if kappa squared is an eigenvalue of the differential operator. So let's make this point. If kappa squared is eval of minus d squared dx squared, then you get singularity, then you get ill-posedness. So this, of course, has to do with resonances of physical systems. If you have, say, a drum skin with a natural resonance, if you load it with a loading frequency that's very close to the resonant one, or at the resonant one, then you're going to get just arbitrarily increasing magnitude until the linear approximation is not valid. And even more problematic, perhaps, is that if kappa squared is close to an eval, the situation is ill-conditioned. Meaning that even if f1 and f0 are very small, you can still have a very large solution. So this is all quite problematic. And it's important to remember when we go to 2D Helmholtz problems. So before we wrap up, let's just talk a little bit about the Yukawa equation as well. So what is the Yukawa equation? It is exactly the same as the Helmholtz equation, you just flip the sign. So Yukawa looks like this, plus kappa squared u is 0, u of 0 is f0, u of 1 is f1. Maybe I should have drawn a representative solution of the Helmholtz equation. So here you have oscillatory solutions to something like this, and you have a characteristic wavelength that is 2 pi over kappa. So if kappa is large, is when things get difficult. Right. So let's return to the Yukawa situation. So here u of x, the general solution looks precisely the same as for Helmholtz. Just you swap out cos and sine for the corresponding hyperbolic functions, like this. So then, what does this typical solution look like? So f0, f1, well, if kappa is large, it turns out that these things just are very boring. They're mostly 0 and flat. In this case, the linear system you get in order to determine A and B looks like this. It's 1, 0. We get cos h kappa. We have sin h kappa. AB is f0, f1. And this is well post. For all kappa. Positive. Right. So, well post solutions. And no oscillations. Right. This is also known as the modified Helmholtz equation. So the point just being that you really need to pay attention to the signs here. So now that we've looked at the 1D problem, let's look at the actual Helmholtz equation in 2 dimensions. So we'll start with an interior problem, again with Dirichlet boundary data, and we will go a little bit quickly. So the most simple thing you can do is to look for a solution in the form of a single layer potential. So we follow things. This works exactly as it does for Laplace. And the properties of the equation are going to be quite similar as well. So the idea here is just to replace the single layer potential for Laplace by the fundamental solution for the Helmholtz equation, which we saw earlier in the class. Looks like that. So it's these Henkel functions, H0. And they are oscillatory. The larger kappa is, the more rapid the oscillations are. And this leads to a BIE that looks just exactly as you would expect. Like this, and this turns out to be ill-conditioned, just like Laplace. So it's well post, but ill-conditioned. There turns out to be a quirk to that, but it's ill-conditioned. Just like Laplace. And the fix is the same, so almost. There is a quirk with the Helmholtz equation, which we will get to shortly. So next, let's write down the ansatz for a Helmholtz double layer potential. And now the double layer kernel, I'll write it like this. You can evaluate it numerically. You have to figure out how to differentiate the Henkel function and so on. It's a little messy, but it's in principle not complicated. So this leads to a boundary integral equation. So observe here that, so this is an important point. The singularity of this function, for small x and y, this behaves exactly like it does for the Laplace equation, which it must, right? Because at very small distances, the second term doesn't really matter much. So the singular behavior at the origin has to be the same between Laplace and Helmholtz, and that's why all of these equations are more or less, to some degree, the boundary integral equation formulations for Helmholtz very closely mimic the situation for Laplace. So the boundary integral equation we get in this case, it looks the same. So this is a second-kind Fredholm equation, which is very nice. So this is something we're very happy about. So it's well conditioned. Typically, all right, so I've been hedging a little bit here. What do I mean by the well? What do I mean by the typically? And the problem is that you can have this thing that's called artificial resonances. So the BIE turns out to be ill-posed. For certain kappa for which the PDE is fine. So this is what's known as an artificial resonance, or spurious resonance. And there's a standard fix for this, which leads us to the third way of formulating this as a BIE. And the idea is to look for an ansatz that's somewhere in between the double and the single layer formulations. So basically do a linear combination of them. So this is known as a combined field. Integral equation. So we often set, so there was this parameter eta that I didn't specify what it is. Oftentimes you just pick it as the wave number. It might be minus. I can never remember these things. But if you do this, then the two terms are roughly matched in terms of size. And you can show that, in this case, the BIE is well posed whenever the PD is well posed. So this leads to a second-kind Fredholm equation again. Maybe I'll write this a little abbreviated. And this is the second-kind Fredholm equation. And it is well posed whenever the PDE is well posed. So this is the formulation one typically uses for the Dirichlet problem for the Helmholtz equation. So our final example is the exterior problem for Helmholtz equation, again with Dirichlet boundary data. So in this case, right, so let's make it clear that omega is the exterior domain out here. Right, so in this case, for the Helmholtz equation, we have this rather quirky looking boundary condition at infinity. And this corresponds to, on the one hand, you want to have the appropriate decaying solutions, But it's a little bit more for the Helmholtz equation, because you also want to have, so these model wave propagation problems. And this ensures that you only have waves that in a sense propagate outwards. You don't want to have incoming waves into the problem. And then this is the relevant boundary condition. So this is a radiation condition. And this is actually why we chose as our fundamental solution. There are some different choices for fundamental solution for the Helmholtz equation, but the one that we chose is the one that has precisely only outgoing solutions. So the ansatz in this case, the appropriate ansatz is again the combined field equation. So we'll do u of x is, we'll take the double A potential, which is nice because that's how we get the jump that results in a second kind Fredholm equation. And then we add the single A potential that makes sure that we avoid the artificial resonances. And then the BIE that you get is 1/2 sigma of x plus integral gamma see what we get. Yes, the y, this needs to hold for all x in gamma, like this. And what I'm doing, so if I'm getting my intention here is to have the normal pointing outwards. That's how we get. So before we had a minus, but now the normal points into the domain, so we get some different sign. Again, don't take my word for any of this. Trust the notes, or even better, other people's notes. But here is, at least conceptually, the equation. I just forgot to write. We have to include the Dirichlet data like that. So this is the BIE that we get. And this equation is very, very nice to work with. So let's just repeat the advantages. So we get dimension reduction. So in other words, the number of degrees of freedom scales as 1/h instead of 1/h squared if you discretize the exterior domain. You have a well-conditioned equation. And in fact, the second kind Fredholm. And then we have that the radiation condition is satisfied automatically. And you have finite domain. So this is all very appealing. The drawbacks, as I believe I mentioned earlier, again, you get a dense linear system. Because the operators you discretize are global, and you have some issues with kernel singularities. And then just infrastructure. There's much less infrastructure for these types of methods. By infrastructure, I mean that if you want to go and just use readily available codes, there's just less than there is for finite element methods. But again, this is a challenging problem to solve by discretizing the PDE. You really would have to impose some sort of artificial boundary out here, and then we have various types of absorbing boundary conditions, radiating, and so on. So it is tricky. However you do this, it's going to be tricky, but the formulation through a boundary integral equation is one of the more appealing ones.